NVIDIA Jetson Xavier and Orin are at the heart of modern edge AI, compact yet incredibly powerful modules designed to run complex AI workloads right where the data is generated. From autonomous robots and drones to smart cameras and industrial IoT systems, Jetson platforms deliver GPU accelerated AI performance in a small, energy efficient package. In this lesson, we'll explore their hardware capabilities, performance benchmarks, and the real world applications that make them essential for edge AI deployments. Edge AI means processing data right at source, whether that's a factory floor, a drone in flight, or a camera on the street. The Jetson family includes Nano, TX2, Xavier, and the latest Orin series. These boards combine a GPU for AI inference, a CPU for general computation, and specialized AI accelerators in a single module. All Jetson devices run the NVIDIA Jetpack SDK, which includes libraries for AI inference, computer vision, and multimedia processing. And importantly, Jetson is fully compatible with tools like TensorRT, DeepStream, and the TAO toolkit, making development consistent with NVIDIA's cloud and data center platforms. Jetson Xavier comes in two main flavors: Xavier NX for compact, lower power designs, and Xavier AGX for high-performance edge computing. It can deliver up to 32 trillion operations per second, tops, of AI performance, with a 6-core Caramel ARM CPU and a 512-core Volta GPU equipped with tensor cores for deep learning acceleration. It's a favorite in robotics, autonomous guided vehicles, and industrial control systems. Xavier supports multiple camera inputs and high-speed interfaces, enabling AI workloads that rely on rich sensor data. The Jetson Orin platform is the next evolution in NVIDIA's edge AI hardware, delivering up to 275 TOPS, almost 9 times the performance of Xavier. It features a 12-core ARM Cortex A78AE CPU and an Ampere architecture GPU with tensor cores. Orin comes in several variants: Orin Nano for ultra-low power applications, Orin NX for compact yet powerful deployments, and Orin AGX for maximum performance. With a focus on energy efficiency, Orin is perfect for mobile robotics, aerial drones, and edge devices that run on battery or solar power. Despite their differences in performance, both XVI and Orin share a common software foundation. They run the Jetpack SDK, which includes CUDA for GPU programming, CUDNN for deep learning, and TensorRT for inference optimization. For real-time video analytics, the DeepStream SDK comes pre-integrated, and Rapids provides GPU acceleration for data science workloads. Robotics developers will appreciate built-in ROS/ROS2 compatibility, and since both platforms run on Ubuntu LTS, integrating them into existing Linux workflows is straightforward. Jetson Xavier and Orin shine in applications where real-time AI is essential. In warehouses, autonomous mobile robots use Jetson for navigation and object detection. AI drones leverage Jetson for inspection, delivery, and mapping. Smart cities deploy Jetson-powered cameras for traffic analytics and public safety. In industrial IoT, they power predictive maintenance systems by analyzing sensor and machine data locally. And in healthcare, Jetson modules enable real-time medical imaging and diagnostics at the point of care. Choosing between Xavier and Orin depends on performance needs, budget, and deployment environment. Xavier offers a cost-effective, battle-tested solution for many industrial and robotics use cases. Orin delivers cutting-edge performance, making it a future-proof choice for demanding AI workloads. You'll want to consider your power budget, physical form factor, and the complexity of your AI models. Both platforms can scale from single prototypes to full production fleets. NVIDIA TensorRT is a high-performance deep learning inference optimizer and runtime that's built to make your AI models run faster and more efficiently on NVIDIA GPUs, and that includes Jetson devices. In this lesson, we'll go step by step through the process of preparing a model, converting it to TensorRT format, deploying it on Jetson, and tuning it for maximum performance, all while keeping real-world constraints like memory and power in mind. TensorRT is NVIDIA's specialized runtime for deploying AI models at the inference stage. It takes your trained model and optimizes it for NVIDIA hardware, reordering layers, fusing operations, and reducing precision to accelerate computation without sacrificing accuracy. It supports standard model formats like ON and X, as well as TensorFlow and PyTorch exports. On Jetson, TensorRT is built directly into the Jetpack SDK, meaning you don't need extra installations to start using it. The deployment workflow starts with training your model, usually on a workstation or cloud GPU. You then export that model into the ONX format, which is widely supported. Next, you transfer the ONX model to your Jetson device and convert it into a TensorRT engine file. Once you have the engine, you can run inference directly on the Jetson hardware. Finally, you fine-tune performance by experimenting with precision modes and batch sizes. TensorRT provides two main ways to convert a model: the TRT-EXE command line tool and the Python API. TRT-EXE is quick for basic conversion. You specify the ONNX file, choose your precision, and save the resulting .trt engine. Using FP16 precision often strikes the right balance between speed and accuracy, while INT8 can offer even greater speed and efficiency, but requires calibration data to maintain accuracy. Once the TensorRT engine is created, you load it into your application using either Python or C++. The TensorRT runtime then executes the model efficiently on Jetson's GPU and AI accelerators. You can run inference as part of your own Python scripts or integrate it directly with the DeepStream SDK for handling real-time video streams. To maximize performance on Jetson, consider using reduced precision, FP16 or INT8, since they speed up inference without major accuracy loss. Batch processing can further increase throughput if your application allows it. The TRT-EXE tool has profiling options to help identify bottlenecks. If memory is an issue, prune or quantize your model before deployment. And for benchmarking, run pseudo Jetson clocks to set all cores to their maximum frequency. TensorRT on Jetson powers a wide range of applications. Drones use it for onboard object detection in real time. Delivery robots rely on it for navigation and obstacle avoidance. Manufacturers use it for predictive maintenance by analyzing sensor and image data locally. In healthcare, Jetson devices run TensorRT optimized models for edge-based diagnostics. And in retail, AI cameras use TensorRT to analyze customer behavior in real time without sending sensitive data to the cloud. AI at the edge becomes truly powerful when it can combine multiple streams of data: video, audio, temperature, vibration, GPS, and more into a single intelligent pipeline. In this lesson, we'll learn how to connect IoT sensor feeds to our Jetson-powered AI applications using protocols like MQTT, Kafka, and direct API integration. You'll see how to fuse sensor data with AI model outputs to create richer insights for real-world decision-making. Integrating IoT sensors into AI pipelines allows models to work with context, not just isolated data streams. A camera detecting a hot surface warning label could be paired with a temperature sensor reading to confirm an overheating event. By cross-referencing different inputs, such as vibration plus acoustic data, you reduce false positives. The result is multimodal AI capable of predictive maintenance, anomaly detection, and automated control in real time. Depending on your application, IoT sensors can capture a wide variety of data. Environmental sensors track temperature, humidity, and air quality. Motion sensors such as accelerometers and gyroscopes capture vibration patterns useful for detecting anomalies in machinery. GPS, RFID, and beacon systems enable location tracking. Industrial machines often use pressure and current sensors for operational health monitoring. And in advanced robotics or autonomous vehicles, LiDAR, ultrasonic, and radar sensors provide depth and distance perception. IoT data needs a reliable way to reach your AI pipeline. MQTT is lightweight and perfect for constrained devices, using a publish/subscribe model to broadcast sensor updates. Kafka is better suited for high-volume, distributed event streaming. For real-time dashboards or two-way communication, WebSockets are effective. REST APIs offer a flexible request response model, while gRPC provides high performance binary messaging for low latency AI inference communication. Data fusion is the process of combining multiple sources of information so that AI models can analyze them together. This requires synchronizing all inputs, camera frames, sensor readings, using timestamps. Pre-processing ensures data formats match model requirements, such as scaling sensor values or resizing images. The fused data can be merged into a single feature vector and fed to the model. You might also store it in a time series database like InfluxDB or TimescaleDB for historical analysis or future model training. Here's an example. IoT sensors publish readings to an MQTT broker. A Jetson device subscribes to relevant topics and simultaneously processes live video through an AI model. When both video and sensor inputs indicate an anomaly, for example, a conveyor belt overheating, the pipeline triggers automated actions, like shutting down equipment. The results are then pushed to a cloud database for storage and further analytics. In smart factories, video analytics can be paired with vibration sensors to detect potential failures before they happen. Smart cities integrate traffic cameras with environmental sensors to optimize urban flow while monitoring pollution. Agriculture systems combine drone imagery with soil moisture readings to guide irrigation. The energy sector uses video inspection plus pressure sensors to monitor pipelines. And in healthcare, AI can analyze patient vitals from wearables alongside camera feeds for real-time health assessments. Once you've deployed AI workloads to Jetson devices at the edge, the real challenge begins, keeping them running reliably, securely, and up to date. In this lesson, we'll explore tools and strategies for remote monitoring, over-the-air OTA updates, fleet management, and real-time health checks. These practices are essential for scaling from one prototype device to hundreds or even thousands of production edge nodes. Edge AI systems often operate in remote or hard-to-reach locations, warehouses, outdoor sites, or even moving vehicles. Your AI models will evolve as new training data becomes available, meaning you need to push updates regularly. Without proper monitoring, devices may drift in performance, causing inaccurate predictions. Remote management reduces the cost and effort of sending technicians on site for every change. Monitoring starts with tracking device health metrics, CPU, GPU, and memory utilization to catch hardware issues early. You also want to track AI performance metrics like inference latency and accuracy drift. In IoT scenarios, data pipeline issues such as dropped frames or sensor connection failures can break the system. Network reliability is equally critical, especially for devices that push data to the cloud. Finally, logging errors and restart events helps pinpoint recurring issues. NVIDIA Fleet Command is a purpose-built platform for managing and monitoring fleets of Jetson-powered edge devices. For more customizable setups, Prometheus and Grafana can collect metrics and create real-time dashboards. Lightweight Kubernetes distributions like K3s allow for container orchestration on the edge. Balena Cloud focuses on IoT OTA updates, while AWS IoT device management provides a cloud-native approach for large-scale deployments. Updating models at the edge is easiest when they're containerized. You can store optimized TensorRT engines in the NVIDIA NGC registry or a private container registry. Using semantic version tags ensures you can roll back to a previous version if the update fails. Rolling updates allow some devices to stay online, while others update, avoiding downtime. For large deployments, a CI/CD pipeline can automate this entire process. OTA updates are just for models. Your Jetsons OS and Jetpack SDK also need regular updates for security and feature improvements. Always test these updates in a staging environment first. Schedule updates during low traffic periods to minimize disruptions, and keep rollback images ready in case something goes wrong during the upgrade. Automation is your friend when managing edge AI at scale. Set up alerts for performance anomalies and hardware issues. Use end-to-end encryption to protect both data in transit and stored logs. Keep models lightweight to speed up deployments and reduce bandwidth usage. Adopt a GitOps approach for tracking every change to your models and configurations. And before rolling updates to the full fleet, test them on a small number of Canary devices.